Let's start by reviewing some of the different symmetries. I'll show you several geometries, most of which appeared in the notes for reading assignment 5. And for all those symmetries, I'm going to discuss what kind of symmetry is present, and I'll sketch the field and also show you what a good choice of Empyrean contour is for applying Stokes' theorem. Now let me remind you that Stokes' theorem looks like this. You have your contour integral of a vector field is equal to the flux of the curl of the vector field F through the surface S, where the surface S needs to have the same orientation as the contour by the right-hand rule. So your fingers would align with the contour and your thumb should align with the normal vector to the surface. Now in most of the problems, I mean actually in all of the problems for this topic, you will be given this J, or you'll be asked to find J, for example, which is the curl of the vector field F. So your problem setup would look like the governing equation would look like this. This would be the right-hand side and this would be the left-hand side. Okay, let's discuss the geometries. For this case, this is a slab. Your vector field would look something like this. So all of those currents would produce the field that would go based on the right-hand rule. You would imagine aligning your thumb to the current and your fingers would curl around this current density, producing the field like this. On a trace, this would look like this. Your F would go in the negative y direction here and positive y direction here. And then inside the contour also something similar will happen, right? Okay, so a good contour for this case is a contour that will capture J, so it would have a normal vector that's parallel to the direction of the current density. And also, another feature of a good Empyrean contour is that the contour aligns with the field on some of its portions and is perpendicular to the field on the other portions. This makes everything much easier to integrate. The kind of symmetry that's present in this problem is planar symmetry, and it's discussed in section 4.1. The next kind of symmetry is, well, geometry is like this. You have a cylinder. You see the way I drew the current. This is not a shell. This is a cylinder with some sort of volume current density, current flux density. The field produced would go around this cylinder like this. Again, by the right-hand rule, your fingers would align with the field and your thumb would align with the current. And then here it would look something like this. A good Empyrean contour is, again, the one that captures the current density. So it would be a circle in this case. In this case, the symmetry is cylindrical because nothing depends on theta and nothing depends on z. And the only sort of important variable in this case is the distance from the z-axis. And the kind of current that we have here is the axial current flux density. There is another option. The reason why I'm specifying the kind of current density is because in a cylinder, you could also have a situation like this, where the current is flowing circumferentially. Okay. So, and this is discussed in section 4.2. In section 4.3, you have geometries like this one. This is an infinite axial helix. This infinite helix. The kind of current density you have is circumferential current flux density because it goes sort of around the circumference instead of going like it did in this problem. The field produced would be like this. The field produced, you could imagine aligning your thumb to the current density, and as a result, your field would go like this. Now, I want to mention there will not be any field outside of this helix. We had a discussion in tutorial 8 about why this is the case and why it's a very good assumption to have this. Here, this is how this looks like. This is the field. Field outside is 0. And the contour you would set up would again capture your current density. You could set it up in either counterclockwise direction on this trace or clockwise direction on this trace. It doesn't really matter as long as you're consistent and very careful. Yes. And this is discussed in section 4.3. Also in section 4.3, there is a bit of discussion about other kinds of cylindrical geometries where the current is circumferential. One of those would be when instead of this helical kind of geometry, you just have a sheet of current. That's another possibility. You could also have, which I'm not showing here, you could also have shell with current that's not thin. So you would have some sort of thickness to the shell. And then instead of surface current, you would have a volume current density that's distributed over some volume. But that's not what I'm showing here. Here I'm just showing a shell. In a shell, the current would look very similar to the infinite helix. Sorry, I meant the field would look very similar to the infinite helix. And the contour you set up would also be the same. Now, two things I want to emphasize. First, how I got the direction, again, by the right-hand rule. You see this current goes out of the page. And if you imagine aligning your thumb to the current, your fingers would align with the field. That's one thing. Second thing is that actually the fact that I said this and this are very similar, this is kind of an approximation, right? Because in this case, this is really a sheet of current. In this case, we're pretending that our field looks like it's a sheet of current and that it doesn't see those individual wires, right? And this is what we discussed a bit in tutorial 8. In section 4.4, there is a discussion about toroidal helices. Those are similar to axial helices, but they're instead wound on a toroidal form. So you would imagine this donut-shaped object, and then there is a wire that's wrapped around it, and there is a current, wrong pen, color, there you go, current that is passing through this wire. The trace would look like this. Here you see coming out of the page are these wires because they are on the inner circle, because on the inner circle J is coming out of the page. Then on the opposite side, the wires are going into the page. The field produced by the torus will be somewhat similar to the field produced by the helix. So it also goes sort of inside the helix. And is 0 outside the helix. The way I got this direction, again, is by the right-hand rule. Your thumb would be aligned with the wires, and the rest of your fingers will be aligned with the field. So this is the field F, and outside it's 0. Now, the contour that you would select for this problem is going to be the one that captures the current nicely. So it would, the normal vector to the surface, corresponding surface, would be in the same direction, or would be aligned with the current. You could make it same direction or opposite direction, but you just want to make sure that you're capturing the currents. So this would be your contour, for example, in this direction. You also want your contour to be aligned with the field, right? And this is the normal vector I was talking about. In the same section, there is a discussion about circumferential sheet current flux density that's going around a torus. So it's exactly the same kind of situation. The only difference is that instead of having a helix with wires, you have you would have a surface current that's going on this shell like this. The cross section, the trace would look very similar. I just drew these circles here to sort of show that it's a shell instead of individual wires. But really, I could have just copy-pasted the same image because there is really not much difference. The field is also going to be in the same direction, and you would want to choose the same contours. So the field is going like this. Outside is 0. And your contours would be circles that have a surface that captures the current. So circles that go inside of this shell. Here I'm showing a dotted line because it's inside of the shell, so you can't see it technically. You could also have a situation where where your problem is not symmetric, but it's made up of symmetric objects. For example, this problem, one of the objects you have has this kind of current density, so it's axial current density. Actually, let me draw it with colors so that you can see which field is produced by what. Maybe I'll choose brown for this guy. So this is the current, and the field produced is in this direction. Another object you have has circumferential current density. So that's a totally different story, because you can't reuse the same kind of contours for different types of objects, right? For different types of symmetries. So this one has this kind of J, and the field produced is going to be like this. So this would be F1, and the brown one is F2. In tutorial 8, there was quite a lot of discussion about superposition, so you can go back and check what that was all about. And let me show you, in case you're not convinced the contours should be different. You see, this is the contour for circumferential current density. And for the axial current density, this is the kind of contour. Because you want to make sure that your current actually passes through your contour. Otherwise, you're just not going to enclose any current, and your Stokes theorem application would just not give you the right conclusions. Like, it just would be inconclusive, if anything, or you might make a mistake. I'm going to now explain how you could get the current density of a toroidal helix, but I will just do it for the xy plane, so for z equals 0. Now you could get also the current flux density for other values of z, but and there is a bit of a discussion in the reading assignment on how to do that, but it gets a little bit more tricky, so I'll just do the xy plane case. So first, let's talk about current flux density for a filament with some current I that goes in the z direction. So we have just the xy plane. Let me use black. We have the xy plane. And we have a filament that's aligned with the z-axis. So it's piercing the xy plane. The expression of the current density will look like this. It would involve two delta functions to make it filament. You see the peaks happen at x equals 0 and y equals 0, exactly where we want the delta function, exactly where we want the current density to be non-zero. And there is this scaling factor of I. The units of current flux density are always amps per meter squared. Let's check that this expression makes sense. For this, let's integrate J over some sort of a patch on the xy plane. So let's find the flux through this patch in the z direction. So the orientation of this patch is n hat equals z hat. Integrating this, we get the following. We have J dotted with ds. Since our J is in the z direction and ds is also in the z direction, the dot product is going to be like this. It's magnitude of J, magnitude of ds, which makes it a differential surface element, and then cosine of the angle between the two vectors. And since the two vectors are directed in the same way, we have the cosine equal to 1. So we're left with this. That's what I wrote here. So this is magnitude of J ds. Next, I'm integrating this over dy dx. This is the magnitude of this current density. You see, I'm just dropping z hat, assuming that I is positive. And these bounds are just the values x and y bounds for this patch. Then I split the integral into 2 and shifted out the I, and then I get that this integral equals to 1, and this integral equals to 1, so I get I. So everything is correct. It makes sense. Now, if you want the filament to be shifted to some value x equals x naught and y equals y naught, then your current density is going to look like this. So we would have this x naught shift and this y naught shift. This will make our filament, instead of being at x, y equals 0, is going to pierce the xy plane at some other value. Now for the toroidal helix, let's first describe the helix. It will have b turns in total, and it would have, once you draw the xy trace, it would have 2 radii. The inner radius would be r inner, right here. The outer radius is r outer. Now the reason why we have these 2 rings is because, well, if you imagine slicing this torus, you're going to get inner and outer rings, and on the inside, the way I'm drawing the current here, the filaments are going to come out of the page, and they are going to go into the page on the outer circle. Now, if you're just talking about the points on the xy plane, all you see is just a bunch of filaments going up or going down, right? You don't see the way that the filaments are curving when you change the value of z. All you see is just up or down filaments. Now, I'm making an approximation here. I'm assuming that the filament is tightly wound, because if that's not the case, then the direction won't be z hat or negative z hat for the filament. But in this case, if we have this assumption of tight windings, then we can assume that all we have is just the same kind of filaments as I described here, with z hat or negative z hat direction. So then the expression for the current density on the xy plane is going to be very similar to this expression for a filament that I wrote here, but it will you will need to describe it for all the filaments that you have. So you have n filaments piercing the xy plane on the inner circle. You see they're indexed from 0 to n minus 1. The coordinates at which they pierce the xy plane are x inner I and y inner I. And then the same thing for the outer ring, but you see that there is this negative sign. This negative sign is here because on the outer ring, the piercing is into the page. So because, or we could say because the current flows in the negative z hat direction. Because direction is negative z hat instead of z hat. Okay, so this is the expression, but we don't know yet what these guys are. What are these? Y outer, I, X outer, I, and same for inner. So what we want to do is we want to determine the exact expressions for these guys, and once we do that, we just plug everything in and just write out the expression. The location for, let's start with the locations for the inner circle. So it's going to be these guys. Let's just pick one of these. This is going to be I equals 0, etc. This is some I equals something. There is going to be, you see this line makes some sort of angle with the x-axis. Let's call it theta inner I. And it's located at a distance r inner, right? At a distance from the 0, 0 point. This is what I wrote here. So to solve for the x-coordinate of this point, we need to do r inner times the cosine of this angle, right? This is what I wrote here. For the y-coordinate, it's the same thing, but with the sine, right? Because it's vertical. So when we take a projection, we're going to get r inner times sine of this angle. Now we are almost done, but we don't know what these guys are. So this is what I wrote here. We know that the angular distance between these filaments is the same, right? And we know what it is. So here, I wrote exactly that. It goes up with some sort of intervals, delta theta inner, where this delta theta inner is equal to 2 pi divided by the number of filaments. Because in total, there is a full circle, which is 2 pi radians, but then there is n filaments, right? So since there is n filaments, the angular distance between each pair of the filaments is going to be 2 pi divided by b, because there is b filaments, so there is b intervals between the filaments. So there is that, and now I've also added some sort of a shift because we're not guaranteed that the 0th filament is going to be exactly on the x-axis. If we have a situation where the 0th filament is shifted by some amount, then there is going to be this just constant value here. It could be 5 degrees, or let's say radians, like 0.1 radian or something like this. But you could just make it 0. Just keeping this guy makes it a little bit more general, because it lets you, gives you freedom of where the 0th filament pierces the xy plane, and then the rest are just separated by this 2 pi over b. Then here, all I did, I just plugged in 2 pi over b. We get 2 pi I over b plus this shift here. For the outer ring, we have the same thing. The only difference is all those inner subscripts are going to be replaced with outer, right? So this, now we can just plug everything back into this expression here. And this gives us the final result. We get, you see this thing I copied over here, and I plugged in the x coordinate. Let me actually highlight it. I think it's easier. So this x inner is here, and I've plugged it in over here. And then you see this theta inner I is what I'm plugging in here. I got this expression. Then this y inner I is described here, and this is what I wrote here. For the outer ring, I didn't write out the expressions, but they're very similar. The only difference is that instead of inner, you have outer radius, you have outer theta, because you see, they don't have to be at the same angle, this filament and this filament, theoretically, even though actually the way it's drawn here, they are just at angle equals 0. Actually, in the notes, there is no shift. In the notes, this theta inner is chosen to be 0. So this equals 0 radians in the notes. And the same thing here. Okay, so now let's solve a problem that will use this result. So this would be problem number 8 in section 4.6 of reading assignment 5. The problem has two objects involved. One is the toroidal helix that is bisected by the xy plane. The full picture would look something like this. We have this toroidal helix. Well, it's supposed to be tightly wound, but I don't want to draw all the wires. And the xy plane bisects this helix. The current density associated with this toroidal helix is JA. It's measured in amps per meter squared. The pitch of the toroidal helix is 1 turn per 2 pi divided by n radians. So every this many radians, there is 1 turn. When you draw the xy trace, the one that's shown here, you get inner radius and outer radius. So you have 2 rings where the wires are piercing the xy plane. The inner radius is R1, the outer radius is R2. The current flux in the wire is IA, and it's measured in amps. And you're also given that when you look at the XY trace, the current density is coming out of the page on the outer ring. So at R equals to R2. And then on the inner ring, it's going to go into the page. The second object is a filamentary contour that's aligned with the z-axis. So in 3 dimensions, it would look something like this. This is the second object. The current density associated with this conductor is JB equal to I naught, some constant I naught, delta R divided by pi R, and it's in the z hat direction, or maybe negative depending on what the sign of this guy is. Again, it's measured in amps per meter squared. So this is this filament over here that's piercing the page. You're also given that F, the field F produced by these two objects together, is equal to 0 for R equal to R3 on the xy plane, where R3 is between inner radius of the torus and the outer radius. So for some R3, let me make this R3 instead of R. For some R3 that's inside of this torus on the xy plane, the field is 0. And the question asks to solve for this constant IA, so the current in the wire of the torus, as a function of this constant I naught and the number of turns in the toroidal helix. Oh, by the way, sorry, you weren't told yet that this is the number of turns. Turns out it is, but for now, let's just assume that this is some constant that's involved in the description of this pitch. You could think pitch times pitch divided by 2 pi and, okay, I guess 1 over that. And then you're also told that the relationship between the field and the current density is given by this. So curl of F equals to J. So this is some physics law, which really looks like Ampere's law, describing this field. Now, we don't want to use this form. We would want to use Stokes' theorem. Stokes' theorem says that contour integral f dot ds is equal to the flux of curl of f. But curl of f is j, so we get this. We get flux of j. So this is what we're going to be using to solve this problem. Now there is two objects. They look quite different. So let's use superposition to solve the problem. Seems like a reasonable strategy. The first step then is going to be finding the field FA that's created by the toroidal helix at this location where we're looking for the field. I've highlighted here what I'm talking about. Let me switch to purple. So everything that's purple is now the only thing that exists in the universe because we're using superposition and we're forgetting about the filament. We only remember about the helix now. Let's make an assumption on the field that's produced by the helix in the xy plane. We are going to assume that the field is like this. Let's use the right-hand rule. Let's align our thumb with this current. Then inside of the helix, we are going to get a field like this. Same thing will be the case if you consider this filament. Aligning your thumb with this filament will produce field like this inside the helix. As I explained earlier, the field outside of the helix is actually 0. So this is the field. So then we can assume that it's in the plus or minus theta hat direction. Whether it's plus or minus depends on the sign of this quantity. And this scalar, so this would be the theta component of the field, depends only on the distance from the z-axis. Actually, I'm going to say from 0, 0, because we really are talking about xy plane only, because this expression is only valid on the xy plane. Because you imagine when you increase your z coordinate, let's say here, imagine you're somewhere here, you increase your z coordinate, you go outside of the helix. So clearly the picture is changing. So but by looking at the xy plane, we no longer talk about z coordinate at all. Z is completely irrelevant. So now we're just talking about this case. Okay, so this is expression for FA. Let's set up the Amperian contour to apply the Stokes theorem. We will make it a circle in the xy plane. Let's make the radius equal to R3, because remember R3 is where we're told that the total field is 0. So we want our field at R equals R3. So this is the contour. Let's make the orientation counterclockwise, but it's actually completely up to you whether you want it clockwise or counterclockwise. It's as long as you're consistent, everything is fine. So let's make it this way. Then ds is going to be out of the page. Left-hand side of Stokes' theorem is this contour integral of the field. Here, what I did is I took this expression and I plugged it in. But that's not all. I also evaluated it at the contour. So on this contour, R is no longer arbitrary, it's equal to R3, right? That's why I plugged in this guy. And then this is the same as before. Now, this theta hat dotted with ds, let's see what it is. Theta hat is in this direction, right? Well, let me actually, so this is the picture on the contour. Theta hat is in this direction. ds is also in the same direction. This means that the dot product is going to be magnitude of theta hat, magnitude of ds, which is just the length element, the scalar length element, times the cosine of the angle between the two. Since the vectors are parallel, this is just 1. Not just parallel, but in the same direction instead of being the opposite direction. So then this is what I wrote here. I just replaced this guy with ds. Next, I took this out of the integral because this guy has been evaluated at r equals to r3, so now it just becomes a constant, right? It's no longer a function of anything. This is here, and then we have this integral that's left, and this is the expression for the length of this contour, which is equal to 2 pi r3, because it's a circumference of the circle. This is how you simplify the left-hand side. Now let's move on to the right-hand side. Here I copied the xy trace and the contour and the surface over which we're going to find the flux. There is 2 ways to evaluate flux of JA. One is using the current flux density, so we're going to write out the current flux density for the toroidal helix on the xy plane, which I explained a few minutes ago how to do. And then we're going to find the flux of that, I guess, function, well, of this current density. First, we will need the number of turns in this helix so that we can write the integral. Sorry, not the integral, so that we can write the current density. I claim that this is equal to n. The reason why is this. We were told that the pitch of the helix is 1 turn per 2 pi over n radians. If I multiply both sides by n, I will get n turns per 2 pi radians. So n turns per circle, per full circle. So this is how I got this n. Now I wrote here the expression that looks very much similar to the one before. Let me just highlight some things. Here we have, on this line we have the terms corresponding to the inner ring. So these filaments right here. The reason why is because this is R1, so the inner radius on this trace. I have a negative sign here. The reason why is because the direction is negative z hat instead of being z hat, because the current is going into the page here. For the outer ring, I have plus because it's going out of the page, and R2 is the radius. And again, these guys are the x and y coordinates of each of these filaments for the inner ring. So as I iterate from I equals 0 to n minus 1, I would describe the current densities of each of these filaments one by one all the way up to this guy, which would be indexed with n minus 1. Okay, so this is the current density. Now let's find the flux. So what I did is I took this and I integrated it. I'm gonna use some obnoxious color because I want to, like, this integral is not part of this density, but what I did is I integrated over the surface and then took a dot product with ds. ds is equal to z hat dy dx, and our integration is going to be over y and x. The next thing I did is I took this integral and I brought it inside of each of the summations. So this is what I have here in the end. I'm actually going to erase this because I don't want this to be in your notes because j is not equal to the integral. So this was just to show you what I'm doing. Okay, so we have this summation of this integral. Our x is going to go from negative R3 to R3, and y will go from negative square root of R3 squared minus x squared to the square root of R3 squared minus x squared. And the same thing here. Oops. Now let's simplify this integral and evaluate what it is. This z hat dot z hat is 1. Same thing here. This guy is just a constant, and what we really have is a delta function that's shifted to some coordinate x naught and y naught. Now this coordinate changes as I iterate through different filaments, but let's just consider for now this integration for one of the filaments, so for one of the values of I. So let's forget about the fact that we have a whole bunch of filaments, and just for a minute, imagine that all we have is this xy plane, some filament on the inner ring, that's indexed with I, and it has coordinates x naught, y naught. And what we also have is the surface over which we're integrating this expression over here. So I guess, let me highlight it. We're integrating this guy. So let's understand what this integral is. Our surface is going like this. The radius of the surface is greater than R1. Now, this surface, we can think of it as having sort of patches, right? We can break it down into a whole bunch of rectangles. The reason why is because we understand well how delta functions in Cartesian coordinates integrate over rectangular patches. So it's just a little bit easier to visualize. Because we know that when we take the integral of a delta function, shift the delta function from x1 to x2, y1 to y2, so you see this is just a rectangle now, x minus x naught, delta y minus y naught, dy dx. This integral can be separated into two. Sorry, what am I writing? This is similar to what we did in tutorial 8, by the way. So I'm sort of reviewing some parts. Okay, so now you see that if both of these peaks, both x naught and y naught, are captured by these intervals, then the result is 1. If at least one of these peaks is not captured, the result is 0. So we have that if this rectangle captures this, this location, then the result is 1. If it doesn't, for example, we're integrating over this patch, the result is 0, because in this, for example, case, x1 to x2 interval is going to give us result of this guy being 0. So this means what? It means that even though we're integrating over this entire circle, the only patch that matters is this one. So we could just throw away this whole circle and just pretend that the only surface we have is this one, and the integration over this surface is going to give us 1. Well, not really 1, it's going to give us this one, this thing, IA. So then this is equal to IA. Maybe I'll use, I don't know what. Well, I'm referring to this yellow thing. So that the part that's highlighted yellow is equal to IA. And we have minus summation from I going 0 to n minus 1 of IA. And this is what? This is negative IA times n. Now let's move on to this part. So what we're really interested in now is the integration that I'm going to highlight in green. This is almost the same thing as before, but there is one big difference. And the difference is this. So we have this filament, ith filament, and we have our surface, but now the surface doesn't reach the filament. Because remember, this part is for the outer circle, and the surface is smaller than this outer circle. We have the filament, so no matter which patch on this surface we take, we are going to get 0. So this means that when we integrate over the entire surface of this circle, we are going to get 0. So this integral is equal to 0. And this happens for every one of those, for every one of the locations where the wire pierces the page on the outer ring. So actually, what am I doing? Sorry. So this green part is 0, which means that the summation is also 0. So overall, we need to add negative IAN and 0. So this is the right-hand side of the Stokes theorem. Now, the other way to find this, to evaluate the right-hand side, is to use the current flux density directly. How you do this? We know that the current flux in the wire is IA. What does it mean? It means that, let's say we have this wire, and if we were to set up a surface that's oriented the same way as the wire, let me draw a nicer picture here. If we were to set up a surface that's oriented in the same way as, well, not the wire, but the current density, and integrate it and get the flux, then we're going to get flux equal to IA. So what do we have for the actual flux we're calculating? We have a surface that has n wires, the wire piercing it n times. That's why I have this factor of n here. I have the value of the flux, but I also have this negative sign. The reason why is because this is the case when n hat and JA are in the same direction. But we don't have this situation. We have a situation where the flux is, where the current is into the page, but the surface is oriented out of the page. You see this vector is in the z hat direction. That's why instead of plus, we need to take a minus. But basically what I want to show you here is that you don't actually have to go through all these steps. You can just use physical intuition to get this flux. Just make sure you get the sign right and this n factor right, and you should be okay. All right. Next step is to equate left-hand side and right-hand side of Stokes' theorem and solve for unknowns. So we have, oh, it's on the different page. Okay, just trust me on this. We got this for the left-hand side of Stokes' theorem, and this was the right-hand side. So then solving for FA at R3, we get negative IA n divided by this guy, 2 pi R3. This means that our F, which remember was FA, which was equal to, by our assumption, it was equal to this. So then when R equals to R3, our FA equals to this guy at R3, which is right here, and then I just copied it, times theta hat. And remember, this is valid only on the xy plane. Okay, so this is FA. Next step is to find FB. What I drew here is the same XY trace. I've highlighted the filament with green, so now green will correspond to everything that has to do with the filament that, remember, was aligned with the z-axis. And we want to find the field created by this filament at R equals R3. This is a reminder of how the current flux density looks like for this object. Again, we're assuming that F is in the theta hat or negative theta hat direction. So the current created by this filament by the right-hand rule is like this. Sorry, did I say current or field? It should be field. Field created is this. Now, this guy is not just on the xy plane, this is everywhere. And also, this scalar factor depends only on the distance from the z-axis. Again, setting up Amperian contour, we can make it a circle in the xy plane of the same radius as before and the same orientation as before. Since this is superposition, so like we're solving this separately, so you could also choose, let's say, you could choose it in the negative, how to say, in the clockwise direction, so that, you know, just as an exercise. But I will not do that. I'll just make it the same. Okay, so this is our contour. ds is in this direction. Left-hand side of the Stokes theorem looks very similar to before. I just took, oh no, green, should be green. I just took this and plugged it in here. And I also plugged in r equals to r3 because we are on the contour when we're integrating. I took this guy out of the integral. I also realized that theta hat dotted with ds is equal to scalar ds, since they're in the same direction. And then this is what was left, and this is equal to fb at r3 times 2 pi r3. On the right-hand side of Stokes' theorem, we have this integral. Sorry, this should be b. I will fix that if I don't forget. Then I plugged in the expression for jb right here. Direction is z hat. The next thing I did is I realized that this is equal to ds. The reason why, again, is because ds vector is in the z hat direction, so the dot product is positive and is equal to this guy. That's what I got here. Next, I'm integrating over dr and d theta. We do need the Jacobian in this case. It's equal to r. Theta bounds are from 0 to 2 pi because it's a full circle. And r bounds are from 0 to r3. Next, we take this I0 and take it out of the integral. Same thing for pi. R's cancel. So for the r, and then, sorry, for theta integration, we have 2 pi. And for r integration, we're just left with delta of r. So right here. Now remember, delta is a symmetric function, even function. So integrating from 0 to r3 is going to give us 1/2 instead of 1. So the result is I naught. And then we have pi's cancel. 2 cancels with 1/2. So we're actually just left with I naught. Next, equating left and right hand sides. So this guy and this guy, we get this equation. Solving for fb at r3, we get I0 over 2 pi r3. Then at r equals to r3, we have our fb equal to fb at r theta hat but we're plugging in R3, so we get this guy. And theta hat. The third step is to add together the fields produced by the two objects. That's why I shown here, I've highlighted everything, both objects. Not just anywhere, but we want the field just on this circle, r equals to r3 on the xy plane. Here I copied the expression I got just now. This guy was from previous part where we found field from the toroidal helix. Remember, we're told that this field is equal to 0, and we're looking for IA in terms of a bunch of other things. So for this guy to be 0, what do we want? Let's factor out theta hat. Then we get this. And then let's shift this guy. Well, the only way for this to be 0 is that this guy is 0. And if we shift this to the right-hand side and I guess swap left and right-hand sides, we will get this. And then we can cancel 2 pi, we can cancel R3, and we're left with IA equal to I naught divided by n. So this is all. This is all we want from this problem.